everybody. Thank you very much for joining us today for the defense of Jacob on his PhD defense for his work. Jacob actually joined my group a long time ago. He's been a very, very successful graduate student. He came out of Tech, did some interesting work in his master's program. He looked at some work in electrical machines, designed a very, very interesting high torque and high speed generator system. After that, our focus shifted back onto grinding and really trying to understand and sort of pursue an in-depth phenomenological understanding of grinding processes. And that's going to be the focus of the work today. Coming out of the work, there's been a lot of contributions made already. You'll see at the end of the presentation, we list some of the publications that have been made. I also wanted to point out that Jacob's also been very active as a GTA, a teaching assistant at ME 2110, where his contributions have been notable. He's really put a lot of effort and support into that program too. I've asked Jacob to perform the usual extremely difficult task of taking a PhD effort and condense it into 50 minutes. And so we'll see how well we do. You know, our clock's on the wall there. I'll give you a little 5-minute warning, but if we can try and do that, so take it away.
Awesome. Thank you, Dr. Mayer. And thanks everybody for coming. Especially like to thank my junior members for their insight and help with this work. Dr. Ozzie Gamble from Carnegie Mellon is joining us on the laptop. And I'd also like to recognize Professor J.M. Shee in the ISYE department. I had a defense with him last week, some travel. So people like all right, so the title of my thesis is Advanced Process Modeling for Control and Microgrinding of Compliant Structures. All right, so the application, why do we need this? So there's a growing need in the micro part industry for some very hard materials with some high aspect ratio features. And I've given you some examples in a couple of different industries here. And to make these micro high aspect ratio features in hard materials, we have a couple of process needs, including super abrasives, something that's harder than the workpiece itself, some precise control, and then for sustainability purposes, we want to do this without using very large machines, consuming a lot of energy. All right? And I think that high aspect ratio microgrinding fulfills this, and to facilitate that, we need a couple of technology advancements. So I've listed a few at the bottom, and what this work is going to address is really the wheel model and also the process dynamics is what I want to look at. All right, and I'd like to point out that microgrinding itself does not have to be used to make final part geometries, but it's often inserted upstream in the process chain to make tools that then make microfeatures. For example, this copper microchannel heat exchanger here was made by micromilling, and I'm proposing that microgrinding could come up here upstream to actually make those tools. All right, so the outline for today's presentation, I'll go through a quick introduction of microgrinding, and then I'm going to present a stochastic analytic model of the wheel topography, and then move that and show some actual measurement of microgrinding wheels and show how that, whether or not that model is accurate. Then we're going to go to stochastic modeling and measurement of dynamic wheel topography, actual grinding. We're going to end up with some conclusions, a summary, and an outlook of where we go from here. All right, so high aspect ratio microgrinding. This is what it actually looks like. We have a workpiece. By high aspect ratio, I mean a small cross section to a very long workpiece. So a lot of compliance on the workpiece side. And then, of course, microgrinding tools are themselves high aspect ratio, and they're in these ultra high speed spindles that also have a large amount of compliance. All right. So if we model this system dynamically, we have several lumped masses, varying stiffnesses and damping, and then linking these two systems, of course, is this grind force in the middle. So we need to understand a little bit more about that. So the limits of this process are really the stiffness and the fixturing and the tool and the workpiece, and then an ability to control all this compliance and just understanding the system of chatter that's coming from this driving force from the grinding action. All right. So currently we do actually do this, but we do it on very large machine tools. All right. So for example, the grinding of a micro milling cutter is done on very large machines like the Roll-O-Matic over here. And to deal with the compliance, they use a very complicated fixturing system. In fact, in this fixturing system, the workpiece itself is that tiny little pin down there. Right? You can't even see it. Very cumbersome. What we're proposing then is how can we take this macro process to make micro tools and put it on a very small footprint on a micro factory. All right, so currently how they actually achieve this, well, grinding modeling is done by a very advanced user offline. All right, they do some lengthy wheel measurements, characterization of wheel topography, and they use these general mean descriptors of a wheel, such as the average static grip density, the average dynamic grip density, and average cutting force frequency, and actual cutting force, all averages. All right, and then using that, they then set a desired depth of cut, and then the control process for this only operates on the position control of the grinding system. Very limited process control. All right. So the big question I'd like to answer is, can we generate a stochastic model of the grinding process? All right. And can we use that to aid in the ability to control and limit the probability of excessive cutting forces, the probability of different surface finishes? All right. So let's go back to a definition of what microgrinding actually is. All right, so this definition here is presented by Dr. Park and Dr. Liang, Dr. Park's thesis. All right, and so what we're looking at are wheels that have very large grits compared to the actual wheel diameter. All right, so take a macro wheel and then just make the diameter really small, but use the same set of grits. All right, so that's what we're calling the definition of microgrinding. This is really the effect. We're going to find out in stochastic modeling that impacts the process. All right, and so to talk about kind of the hypotheses of what type of complications this might present, if we imagine a milling cutter over here, it has 4 very distinct teeth, very well defined. All right, if we model it, we can get a cutting force for each tooth, and we know pretty much that each of them is going to be about the same. On a macro wheel, there are so many grits that if we model it, we come with a mean or average grit cutting force that pretty much holds for all these grits because the cutting frequencies are such a broad band. It looks like one flat line with a bunch of high frequency wheels. Right? But this microgrinding wheel is somewhere in between. Small wheel, big grits, well-defined cutting edges. All right? But they still have some stochastic characteristics in that their depths of cut are not the same, their cutting edge radius isn't the same. Right? So we're thinking that this is going to cause problems statistically with creating a probabilistic model. And as an example down here, imagine that if you wanted to determine what the average grit diameter is, you go through and measure a bunch of grits and have a predicted mean. All right? But if the wheel has a limited number of grits on it, all right, you have to have an actual confidence interval on how confident you are that this is the actual mean. And so when you have a micro wheel, there's a very small number of grits, so your confidence interval gets very large. Right? There can be a wide range of actual values. All right, so wheel topography has been studied extensively in the community since the 50s. All right, the most common method of doing modeling relies on assuming the wheel has uniformly distributed grits, all with the same grit spacing and with a mean grit protrusion height. And Dr. Malcolm's book covers this very well. And then for super abrasive wheels, in microgrinding, we usually use CBN or diamond, which would be a super abrasive grit category. The most prominent work comes from numerical simulation, such as that presented by Dr. Koshy in the 90s. You can see a results plot of some of his predictions over here. And to move from static wheel topography to actual grinding forces, we currently use a bunch of empirical relationships, all right, and some general geometric propagation of these mean static wheel topography forces, all right. And then we do measure this stuff quite readily, and I've listed some of the prominent methods down here. But for microgrinding wheels, there's only been a limited number of studies, and the most prominent one being imprint methods, where you take the wheel, roll it on a soft piece of material, and put that into a measurement system. And then for on the dynamic side, to measure the actual number of grits that are cutting, the most prominent work by Dr. Park will be using a micro thermocouple and measuring individual heat pulses from each grit. All right, so this is background on the work that has been done. And then for the actual grinding cutting force, Dr. Park in his thesis proposed this cutting force model that divides the deformation zone, say plastic deformation region, and a more plowing region with a varying rate angle. All right, and what he comes up with is a force per grit as a function of its depth of cut. All right, so to generate a probabilistic model of microgrinding, we're going to accept this model of the force for each grit. All right? And go back to the questions about the actual wheel topography itself. All right? So can we generate an analytic model of the stochastic wheel topography, all right, without resorting to numerical simulation? All right? And then also we want to explore what are these scale effects associated with linear grids. All right? We want to know if that actually causes problems. And then would we be able to predict the microdriving forces, all right? And then can we use an in-situ measurement system to aid us in making that more accurate and more reliable? All right, so let's go into this stochastic analytic model real quick. First off, I was mentioning static grid densities and dynamic grid densities. Let's go over a definition of that real quick. Static grid density on the surface of the wheel, number of grids per unit area. All right, but in the driving process,